So good afternoon and welcome to the last Primkulov lecture of the semester. Today our guest is Dr. Bauyrzhan Primkulov, instructor of applied mathematics at MIT. Bauyrzhan obtained his PhD in civil and environmental engineering last year, also from MIT, when he received the award for the best doctoral thesis of the CEE department. His work in modeling two-phase flowing porous media of different electrolytes is very relevant to our research in Primkulov, and I recommend you going through his recent publications. The title of today's talk is Moving Contact Lines Over Heterogeneous Surfaces from Stick Slip to Steady Sliding. And Bauyrzhan, if you're ready, the floor is yours.
Okay. Thank you, Paula. It's a pleasure to be here. I've been enjoying quite a bit of the Primkulov work over the years, and it's really nice to be here to share some of my work. So this work, it started still during my PhD, and it has been a fun project to think about now for over some time now. So let me get to it. So at the early, some of the first experiments that I've been doing, well, this was as a graduate student, they kept bringing up a memory from when I was still quite young. So when I was young, we would take these long drives once a year. Every summer, we would drive to the south part of Kazakhstan. And then, during those ages, there were no smartphones. So when you are in the car, so there are only a few things to do. You talk to people. We used to, sing songs. But then quite a bit of the time, you would actually enjoy the scenery. And because the drive is long, so you would catch rain once in a while, and then you get this, the scene that probably a lot of you would connect with. So whenever it rains and you are somewhere near a window, you would see this pattern of drops that accumulates on the window. And if you watch carefully, you would see that all these drops, they seem to have very different shapes from each other, different sizes. Most of them would be stuck, but then once in a while you would see one or two drops that would slide all the way down to the bottom. And so this problem of drops moving over real imperfect surfaces is something that all of us have a good intuition for. Now, so these years, let's take a step back. So when these trips were taking place, some good work was already done on the subject. And it was interesting. So when I was reading this biography of Degens, I found a small section where he actually described a story related to a problem of these moving contact lines. So he goes somewhere, talks to another professor, and realizes that they've been working on the same problem. So then Degens decides that the problem is important enough that he would like to be the person to share his result first. And he goes to his graduate student, who was Giovanni at that point. So everything is according to this biography. So he goes to his graduate student and tells him, okay, so give me all the notes you have about this problem of contact line hysteresis. Give me your notes, I'll go do the writing, and then you will review it. And at least in the book, the way they describe it is over one evening, they probably worked late into the night, they wrote up the manuscript and then ended up submitting it. And so by the timing of it, it sounds like it should be the a paper from 1984. I would love one day to find out if that's the case. So why I say it, this problem of, it connects to your own common day experiences, but also it's an important enough problem for people like Bauyrzhan and others to be worried about now back in 1984. Well, of course, so it's also a problem that's relevant to porous media flows. And there are all sorts of porous media flows that have contact lines moving in them to a different degree. And there is actually a fun one, a video from Marcel that demonstrates one of the flows that's one of my favorite. Now to more serious applications. So a lot of the geophysical flows involve moving contact lines, and their understanding what happens at the smaller scale would be also useful. Now, in my opinion, while watching the window glass is nice, it's probably much easier to study these droplets moving in a confined environment. So for me, the ideal environment to study these drops and how they move is inside the capillary tube. Because in a certain limit, you can get some of the things to scale linearly. But I'll get to that a bit later. So in a good tradition, I'll start with a warm-up problem that also comes from common experiences. So if you take any sort of porous material, and in here porous material is a biscuit, and you dip it in coffee or tea, you would see that coffee gets deeper into the fiber of the cookie. Now, if you do it in a more controlled manner, so if you take a capillary tube and dip it in any liquid, you would see that the liquid front advances, but then it slows down with time. So then there is this famous scaling that shows up as a result. So Z is the position of the interface, and T is time. So this front propagates in a diffusive manner. Okay, so but then this trend is fairly straightforward to understand. So what's happening is there's some capillary forces at the interface. So in here, I'm thinking about oil and air, and capillary forces pull the fluid inward. And then as the liquid depth becomes larger, it becomes more and more difficult to pull it inwards. As a result, so this fluid front, it slows down with time. Now, what you can do, you can modify this setup slightly and get a lot of nice advantages for free. So the modification is fairly simple. So instead of pulling only oil, what you would do, you would introduce an oil slug and then dip this setup in water. So then what you have is you have air on one side, you have a slug of very viscous silicone oil in the middle, and you have water on the other side. You still get spontaneous imbibition, so the fluid still moves on its own, but then it moves on average at a constant rate. So you go from this diffusive scaling to a linear scaling. So why I like this setup is it gives you a good level of flexibility. So one flexibility that you get here is by simply changing the length of the slug, you're able to control how quickly this front propagates forward, and it propagates linearly. So the longer slugs, they move slower. The other nice thing about this setup is you can write down the force balance also fairly easily. So you have capillary forces, so capillary force at the front meniscus, capillary force at the back meniscus. These forces depend on the angle that the interface makes with the solid surface. So you have one angle at the back, one angle at the front. So those are capillary forces. Then you have, how do I call them? You have dissipative forces, or no, damping forces. Damping forces due to the flow inside the bulk of the viscous fluid. And in this setup, why this whole thing is moving at a constant speed is that all of the action takes place inside the viscous oil. So viscosity of water and viscosity of air, they're negligible compared to viscosity of this silicone oil. So then on the scale of a single capillary tube, it moves at a constant speed. Now you balance these forces, and then you get a relationship between a capillary number, that's the speed at which the slug moves, and dimensions of the slug. So R is the radius and L is the length of the slug. Now, if you knew how both contact angles behaved, you would know exactly how fast this slug would move. Luckily for this setup, so these were clean capillary tubes, both contact angles were well behaved. And then now I'll say what I mean by that. So the silicone oil air interface, so that was fully wetting on this clean glass capillary. And as a result, so if you measure the contact angle versus speed, so versus capillary number, you would see that the front contact angle, it follows nicely a well-known relation. So, so then we know exactly how the front contact angle behaves. And luckily, the one contact angle that's a bit more, usually a bit more difficult, so water-oil contact, water-oil meniscus, in the range of the experiments that we conducted, so that's the blue region, it appeared to be constant. So this is these are the curvatures that we're fitting of the back meniscus. So the back meniscus curvature seems to be constant. And because of that, for this particular experiment, we could write down a relationship between the capillary number and then just these dimensions of the slug. And that allowed to nicely capture the way the slugs would move depending on its dimensions. So the same thing as I said before. So as you go on the x-axis, your slugs become smaller. As you go on the y-axis, your slugs move faster. So smaller slugs move faster. But then you also see the color. So what does this color mean? The red color means that most of the dissipation takes place near the contact line. And in here, it's this contact line of the front meniscus. The blue region, that's a linear regime where most of the dissipation takes place in the bulk of the fluid, where you get well-known Poiseuille flow, and things scale very nicely. Okay, so why did I bring up this warm-up problem? So this warm-up problem, it was done at a constant rate. Oh, sorry, at spontaneous imbibition. So no pressure was applied. It was, moving on its own. So that's the solid line here. But then you could force the same slug to move either a little faster or a little slower if you do two things. So you can either apply external pressure, so a pressure difference across the meniscus, or you could connect one end of the tube to a syringe and drive it at a constant rate. So then this experiment, you can go above or below the line, but you can do that in two fashions. And it turns out the dynamics is somewhat different in two cases. Okay, now what we do exactly that. We start examining this problem where we are driving the system at a either constant rate or a constant force. And these experiments that you see on the right, they are done at a constant rate, so at a constant displacement rate. So that we just connected to a syringe and pushed it at a prescribed velocity. Another twist is while in these experiments, the capillary tube was fairly clean and the back meniscus was well behaved, in here it won't be. So in here, our capillary tube has some roughness, there was some coating done, and the surface now is a bit more rough. So if you do this experiment slowly, you would see something that now should remind you of this, what you would see on a window during the rain. So the back meniscus, the water-oil interface, it actually goes through this stick-slip motion. But then if you take the same tubes and you drive the whole system at a faster rate, you would see that you're back to the smooth motion. So on a window glass, this is typically what you would get for like a very narrow range of drops. This is what you would get for very large drops. So then this is a more complicated problem. That's why it needed a warm-up. But then you can actually nicely capture the main features of the dynamics with a few simple equations. So we'll try to go there.
Bauyrzhan, can I just ask a quick question?
Yeah.
So in this slide there, in the previous slide, if you have like this slow displacement, the point that depends, is it like a up, down, or is it like going around like a circular wave?
Okay, yes. So there is another video that I have. So sometimes it goes like this. So it it looks like it's limping.
Yeah.
But in other occasions, it would actually, it would look like a deepening wave around the circumference.
Because there is no break of symmetry, right, in the model. Like, why would it choose like one direction, like up and down for the limping?
Oh, okay, yeah. So this is experiment. So the whole thing was motivated by some experimental observations. So in actual experiment, there will be breaking of symmetry, as in this roughness that you have on the walls. It's not necessarily axially symmetric.
Right, and that defines what where like the point of limping is.
Yeah. So
Okay.
So that's what I'm guessing.
Okay. Super. Thanks.
Yeah. Thank you. Okay. So now, because this setup is so simple, we can write down nice approximations for all the forces that are involved. The goal here would be to convert this system, where you have an actual slug, into a system like this. So two coupled oscillators. So then we are going to start speaking the language that we've been taught in differential equations. Okay, so one force that we can right away figure out is the externally applied force. So you can have a pressure difference across the meniscus. So that's the pressure difference times the area. Then you would have some damping forces inside the fluid bulk. Plus, I'm going to lump the forces that are related to the well-behaved meniscus. So that's the one that we know. I'm going to assign some force to it. So all of that is going to be lumped into this first object. So that object I'm going to call a slug. Now, what's left? So what's left is all the dynamics that happens at the misbehaving meniscus. So that's the one at the back. So there's some, you can estimate the viscous damping that would take place at the contact line, and it would depend on the mean contact angle. So you can write that down. So there's some damping force. Plus, depending on the type of roughness you face, your contact angle, effective contact angle, like in the video previously, would change in space. So it would limp. So then I'm introducing this this pinning force. Okay, so that would be the second object. So the second object is the contact line. So contact line here is visualized in here. And these two objects, they're connected by a spring. And like it has been pointed out in many situations for drops, interface often can act as a spring. So now you have two objects. One object is the bulk. The other object is the back contact line, and they are connected through this meniscus. So then you can write down the equations. So dissipative forces on the left-hand side, all the other forces on the right-hand side. And that leads you, if you take the forces and divide them over the length of the contact line, you get a system of equations that now starts looking very, very familiar. So it's a spring dashpot model. Spring dashpot model where you have dashpot term, the damping term on the left. So you have first equation is written for the slug, where you have cumulative applied forces per length of the contact line. The second equation, you have some dissipation or some damping in the contact line itself, plus contact line actually is the thing that's in contact with this surface roughness. That's the spinning force, and the two objects are coupled through this spring. So that's all you're seeing here. Now, luckily, this problem, as I said, has been examined before, and there's some nice papers now, again, back from 90s, that actually considered exactly the same equations. So a coupled spring dashpot model. So in this model, what you should pay attention to is ZB, that's the position of the slug. ZC is the position of the contact line. And only the contact line is the object that feels this pinning force. So they've made some really nice observations, some really nice scaling arguments. But then you can actually get recast this system in a very similar system of equations, but that have some advantages. So what we're gonna do, we're gonna take this pinning landscape, and I'm gonna think of it as a sine function. Sine function that has a wavelength, characteristic wavelength of Q. So instead of having disordered pinning, I'm gonna have a very ordered, well-defined pinning. The second thing that we're gonna do is we're gonna rescale this Z axis, so the position along the tube, we are gonna rescale it by this wavelength. Okay, so then we get a system of equations that looks exactly the same. So damping on the left, so the dashpots on the left, and then all the forces on the right-hand side. But then these equations now have an advantage that you can link them to a very nice intuitive analog. So what I'm gonna cover now is I'm gonna show that this setting, so this capillary tube and a slug inside the capillary tube, it's actually equivalent to a pendulum inside the drum that's filled with a viscous fluid. And then you can drive this pendulum in two ways. One way to drive it is you can start rotating the outer edge of the drum. You can start spinning it at an angular velocity omega naught. So if you do that, you will end up moving moving the pendulum. So in here, the omega naught, that corresponds to the externally applied force. The second way you can move it, you can attach a spring to the pendulum, and you can pull the spring at the prescribed angular velocity. And that would correspond in here to pushing the slug with the syringe at the prescribed rate. Okay, so now I'm going to go through each one separately. So now I'll be just thinking about these drums in two different settings. One setting is constant force, the other one is constant rate. So in constant force setting, I have the same system of equations, and I'm just gonna recast it in dimensionless form. So I scale the time by omega naught. Then you have this system of equations where only a few parameters become important. So one parameter is lambda. It roughly tells you how important is, how much smaller is the damping at the contact line is compared to the bulk. Then you have this term, which is roughly a spring stiffness, and then B, which you could think of as pinning strength. So then we are, of course, going to start going to limits that would allow us to get some insight from here. So one limit, I'm going to assume that lambda is very small. That means the damping at the contact line is negligible. So then instead of two equations, we're going to eliminate this spring term, and you get just one equation that governs the position of the contact line. You make another approximation. So you say that this B over K parameter is very small. So then you get this nice equation that's going to be a star of the next few slides. So this equation actually shows up in a few places, and I couldn't resist. So I'm going to say that it also shows up in this nice textbook by Strogatz. So if you go to the textbook, you would see that when he covers these nonlinear oscillators, one of the oscillators has exactly this equation. And people actually have used it as a simple model of how fireflies synchronize. And the idea is also there is quite simple. So fireflies, they have their own natural frequency of flashing. But then if you take a flashlight and flash it at the firefly at a certain frequency, firefly, if these frequencies are close enough, it would try to either move a bit faster to match the flashing, or it would try to, if it's too fast, it would try to slow down to match the flashing. Then in this setup, alpha would stand for the difference between these two frequencies. Okay, but that means this problem is actually well studied. But in our setup, we are thinking of a drum, and we're thinking of a pendulum inside the drum. And in here, you actually get three very nice regimes that you can nicely understand. So if this B over omega parameter is much larger than 1, or if it's larger than 1, then this equation has two fixed points. So one fixed point is this one, the other one is off by pi. And out of these two fixed points, one is stable. So what does it mean? That means if you spin this outer edge of the drum slowly, the pendulum would shift and it would stay at a fixed position. Which means you're not spinning it fast enough to make it go all the way around. So gravity of the pendulum actually is the maximum gravity that pendulum can experience is larger than the force that you're applying through this viscous environment. Now the second limit is now when you push it hard enough, so you're spinning it hard enough that this pendulum would eventually overturn. So for this equation, you can easily calculate the period of oscillations, and you would see that the period of oscillations, it diverges as this parameter approaches 1. So what it tells us is that this pendulum, now in this fine state, what happens, it spends most of its time when the gravity is largest, so that's here, and it zips through the rest of the angles fairly quickly. Now, if you go to the limit when you are spinning this drum at a crazy speed, the viscous forces would dominate, and the pendulum would actually move at the same speed as the outer edge of the drum. So that's also quite easy to understand through the equation. So if you're spinning it fast, this parameter is much smaller than 1. Then this alpha c is equal to 1, which means pendulum is moving at the same speed as the drum edge. And then in that setting, you can see that in the frame of reference, moving at the same angular velocity as the outer edge of the drum, any oscillations, they're supposed to die out. And then, yeah, so you can simulate this nicely, and you would see the same things. So on the y-axis, you see the position of the pendulum. On the x-axis, so that's the time. So the sharpest graph, so the graph with the steepest slopes, that's on the left-hand side, so that's closer to the static mode. And then as you increase the speed, this amplitude of oscillations in this moving frame of reference, so they die out, which means you're going from stick-slip motion to something that looks more like a steady sliding. So the nice thing about this, although all of that was done for a limiting case where we've made a whole bunch of assumptions, assumed a whole bunch of terms to be small, so you get this very different scaling. So you get what I'm plotting here is on the y-axis, I'm plotting the force. On the x-axis, I'm plotting the displacement rate. And the force versus displacement, it scales differently depending on how quickly you are spinning this setup. So you get 2-to-1 scaling versus linear at some point. But even though we've made a whole bunch of assumptions, if you keep track of the same forces and same displacement rates for the actual system of equations, you get almost exactly the same scaling. So then us going to this simplified version was actually not only helpful intuitively, but it helped us figure out the force scalings also quite nicely. And this was already known by Degens and Mark Robbins. We're just showing that it also holds up for a less limiting case. Now I'll go to a bit more interesting setting. So a bit more interesting setting is when you pull this pendulum with the spring, and you're pulling it at a constant fixed angular velocity omega u. So here you can anticipate the dynamics is going to be somewhat different from the constant force setting. So what we're going to do, we start with the same governing equations of motion. We're going to, in this case, go into the frame of reference that moves with the end of the spring. That way, again, just from 2 equations, you reduce the dynamics to a single equation, where now we can start playing around with different limits. So these terms hopefully now look already familiar. So this is a damping term, this is a spring term, and this is a pinning term. Now what we're going to do, we're going to examine this equation in a limit, in the same graphical sense that Degens and people have done before. So what you can do, you can realize that this system is going to behave very differently depending on the relative magnitude of the the spring term and the pinning term. So what I'm plotting in here, so the red line that you see, that's our pinning force, that's periodic, that's sinusoidal. And because of this tau, this pinning function, it moves left with time. And the blue line that you see, that's the spring term. Now, if you think of this motion in a quasi-static limit, this goes to 0. So then the position of the pendulum, it would be defined purely by the balance of spring term and the pinning term. And you right away see the problem. You see that the spring term, in this case, it intersects the pinning function occasionally at more than 1 point. So what does that result into? So if you run the simulations of, so if you evolve this with time, the quasi-static curve of the pendulum position versus time, it corresponds to this steepest curve. So that's the one that I'm outlining right now with the mouse. So you see that the motion is relatively smooth until you reach something people call a desanchoring event. That's an event that's depicted here, where you move very sharply from one stable condition to another stable condition. That's this jump. And then again, you slide along the surface where these two forces are balanced again. Now, in this setting, you can nicely approximate the excess force, excess in relation to the quasi-static limit. So you can approximate the excess force that you would need to apply to move this pendulum. And that excess force would be simply, so I'm zooming in right here. And here, red line is the quasi-static limit. So that's how the interface would move then. And the blue line is how the pendulum would move at basically finite velocity. And the difference between these curves, so that's closely related to the magnitude of the force that you would need to apply to move this pendulum forward. Now, again, people worked out this before. So then they worked out that this excess force that you would need to apply, it scales as 2/3 of the pendulum speed, which is nice. So now a different case is when the spring term is much steeper than the maximum slope of the pinning force. So in that case, it's a smooth behavior, as in spring term and pinning term, they only intersect once at any given time. And suddenly these desanchoring events that I covered in the previous slide, they disappear. Because they disappear, the force scaling is now very different. So instead of power 2/3, you get a linear scaling. So then to summarize this constant rate analog, you get very different regimes depending on the relative magnitude of the spring stiffness to the pinning. So what I'm plotting here is this excess force that you need to apply. On the x-axis, that's the displacement rate. And then depending on this parameter, you get very different scaling between the force and the displacement. Now, when do you go? Well, because we're thinking also of a stick-slip motion, so transition from the stick-slip to something that looks more steady, you will also notice that on both of the curves, as you increase the displacement rate, so how quickly you're pulling the end of the spring, the amplitude of oscillations about the end of the spring, it dies out. And that you can also work out quite easily. So in that limit, when this parameter is large, this equation, you can simplify it, approximate it as that. And that's that's an equation that you see very early in differential equations course. So this is just a spring dashpot oscillator with a periodic forcing in time. It has a very nice solution, a solution that decays, it turns out decays with the speed. So the amplitude of oscillations, they decay with speed, that's this term. But then you also get a transient solution that gives you a very important time scale. And that time scale is nicely demonstrated with this imperfect analog. So don't overthink it. So I'm making a small version of this drum. And this drum, basically, it's like a cup that spins, you put honey in it, and the pendulum that you're forcing is this spoon. So then with this spoon, you can actually, depending on how you mix it, you can get two different regimes. So one regime where pendulum moves at the same speed as the outer edge. The other limit is this stick-slip limit. And the transition between the two in this pendulum analog is exactly that time scale that showed up in the transient solution. So that's this simple parameter. So this simple parameter then is supposed to tell us when our slug transitions from stick-slip motion to something that looks more like a steady sliding. So now I'm trying to go from this drum analog to something that we're interested in from the beginning. So all these parameters, why it was nice to go to that frame of reference where drum analog applies. In that frame of reference, there were only few parameters that were important. So what was important is the pinning, so relative magnitude of pinning to spring stiffness. And the other important parameter is this time scale that showed up. So you would see that you would get very different displacement regimes depending on these two parameters. And you would get a transition from something that looks like a stick-slip motion to something that looks like a steady sliding if this time scale parameter is smaller or bigger than 1. Now, if you go back from this drum analog to the actual capillary tube, you would see that this time scale parameter, it's actually just a rescaled capillary number. And it's rescaled by Q over R, where Q is the wavelength of this roughness that we've assigned, and R is the radius of the tube. So then the natural next step was just to compare these predictions to a cleaner setup where we could exactly impose a nice periodic roughness like that. So then you see a very similar behavior. So as you increase, so if you impose the sinusoidal roughness on the walls of the capillary tube, you would go from something that looks like a stick-slip to something that slides more smoothly if you cross this critical threshold in a capillary number. So that's what we're reporting here. Okay. Now, just to recap what we did in here, we had a simple experiment that motivated the entire study, where initially we saw the slug with misbehaving contact line at the back. So that's a liquid-liquid contact line. And we saw that you could actually nicely convert from equations of motion of this slug into a system of equations that either describes pendulum that's driven by the motion of the outer edge, so that's the constant force analog, or you could think of it as a constant rate analog. So that's when you're pulling the pendulum by the end of a spring. And in both cases, so what I'm plotting here is y-axis, that's the total force that you would need to apply to move this pendulum or a slug at a prescribed speed. And you see that in both cases, the required applied force has very different scaling. And that scaling depends whether you are in the stick slip regime or in a steady sliding regime. And the other thing that you could note also is it's always cheaper to move these slugs at a constant force. And that was actually a fantastic insight that Dejeans, Mark Robbins, Giovanni, and Raphael had back in their early paper. Okay, so why did I bring up these force scalings? I brought up these force scalings because it makes me think of a situation where inside the porous media, you have many slugs, or what do we call them? We call them ganglia flow. So whenever in porous materials, you have lots of droplets moving at a statistically steady state, people in Pore Lab, actually, they've recorded this deviation of this total pressure versus flow rate. So delta P is the pressure applied across the micromodel, and capillary number, that's the displacement rate. So they've recorded a deviation from a linear Darcy scaling. And what all of this business makes me think of is this setting. I could conceptualize it as a system where you have many interfaces moving over imperfect surfaces. So you would have some roughness. And you can expect, depending on the flow rate, you can expect to go from a non-linear scaling of force versus a capillary number to something that looks more linear. And I wonder if the observation that we saw here, if we have pushed it at the higher velocity, if it would eventually turn into something linear. Well, the other side effect of thinking about this contact line problem is that now whenever you see drops on a window glass, hopefully you start imagining these pendulums inside the viscous fluid in your mind. With that, I'm going to stop here, and hopefully there is enough time for questions.